Hello again, and welcome to Advanced Physics for High School students. This is Lesson 8, and it is entitled Friction. We begin by introducing the important ideas and variables associated with friction. We all have some notion of friction from our everyday experience, whether it's warming ourselves by rubbing our hands together, starting a fire by rubbing wood together, or using a friction match, as shown in these diagrams. Friction match basically being a small stick whose tip is coated with phosphorus, creating enough heat to combust a pile of tinder that we've assembled to catch the sparks. Friction is one of the most common forces we'll encounter in physics, and so we begin by looking at the important mathematical variables. First, there is F, the frictional force. Capital F for force, the subscript little f for friction. The direction of the frictional force is opposite the object's motion, or its tendency to move. The force arising from the rubbing of two surfaces that are in contact with each other. One surface exerts the force, and the other surface experiences the force. Another important force is the weight of the object, Fw. The Earth gravitationally pulls the object toward the center of the Earth. The magnitude of the force equals the object's mass times the acceleration due to gravity, g, which happens to be equal to about 10 meters per second squared near the surface of the Earth. If the box on the table has a mass of 5 kilograms, then the magnitude of the weight force is 50 newtons directed downward or toward the center of the Earth. This combination of units, kilograms multiplying meters per second squared, is known as a newton. A third force is the normal force, Fn. By the word normal, we don't mean ordinary, but rather perpendicular. The normal force is exerted by a surface in a direction that is perpendicular to the plane of the surface. In the diagram of the box sitting on the table exerts a normal force on the box that balances the box's weight. The surface of the table is horizontal, and it exerts a vertical force on the box, normal to the plane of the tabletop. Another important variable is the coefficient of friction, which is represented by the Greek letter mu. The coefficient of friction is a number representing the relative slickness or roughness of the surface that we're looking at. The slicker the surfaces are, the lower the mu is. The rougher the surfaces are, the higher is mu. Because we'll be dealing with stationary objects as well as moving objects, we'll need to distinguish between static friction, mu s, and kinetic friction, mu k. When we discuss static frictional forces, we'll use the symbol F with a subscript s. And for kinetic frictional forces, we'll use F with a subscript k. Since frictional forces act between pairs of surfaces, let's examine a surface in this diagram. The surfaces in contact between the bottom of the box and the top of this table. If I enlarge the surfaces in contact, what I'm going to see is that there are rough spots at the microscopic level. Even if the box and the table feel smooth to my touch, the surfaces contain irregularities. If I try to shift one of those surfaces relative to the other, those irregularities will catch on each other and resist the shifting, and this resistance gives rise to what we call the frictional force. I can't measure each point on the surface the force that's due to those individually, but collectively they're going to exert what we call the frictional force. Because we wish to describe the object's motion mathematically, we need to numerically describe the frictional force. So we need to develop a system of representing the forces graphically and quantitatively. So let's return to a sketch of this box on the table. What we'll come to call a free body diagram is what we want to sketch now. A free body diagram is a diagram representing the object as a single point and showing all the forces acting on that single point, usually that point being the center of gravity of the object. So for this box, the box is being pulled downward by the Earth, and we call that the box's weight, Fw. Whenever any force acts, the force connects two objects with each other, in this case the box and the Earth, and there's a direction of that force, and we need to indicate all of those things in the free body diagram. The Earth pulls the box downward. The Earth is the thing that exerts the force, the box is the thing that experiences the force, and the arrow indicates the direction of the force. Developing this technique of identifying two interacting objects and the direction of the force is going to help us in the future when we work with Newton's third law of motion, and so I introduce that idea in this lesson. Incidentally, how it is that the Earth is able to exert this mysterious invisible force that we call gravity is a philosophical question that has puzzled many folks through the ages. For our purposes, we're not going to debate the philosophy, rather we'll describe the forces as we experience them. Now, the weight isn't the only force that the box feels. The box is in equilibrium, which means that the box is not accelerating. It's not changing the way that it's moving. Right now it's motionless. In a couple of minutes, if nothing works on it, it's going to remain motionless. And so that means that there has to be another force, at least another force, acting on the box that balances the weight. That force is exerted on the box by the table. Since the table has a horizontal surface exerting a vertical force, we're going to call this the normal force. The table pushes the box upward. Again, there are two objects. One object is exerting force, the table. The other object is experiencing the force, the box. And there's a direction of the force, upward. Now these two forces, the weight force and the normal force, balance each other. The box isn't accelerating. So numerically, these two forces must be equal in magnitude, and they must be opposite in direction. That important logical fact, that the two forces are numerically equal, becomes important as I begin to monkey with the system by tying a string around the box and pulling on the string. So let's examine that situation. Let's make our box move to the right with a constant velocity. A pulling force acts on the box. The string pulls the box to the right. I'll call that Fp for pulling force. Again, two objects are interacting. The string exerts the force, the box experiences the force, and the direction of the force is to the right. We still have the box's weight. The Earth pulls the box downward. We still have the normal force. The table pushes the box upward. The table is a horizontal surface. It's exerting a vertical force. The direction of the force is perpendicular to the direction of the surface. That perpendicular force is what we call the normal force. Finally, because the box is not accelerating, then something must balance the pulling force, and that something is the frictional force. The surface of the table, the irregularities between the tabletop and the bottom of the box, will push the box towards the left. Because the box is in equilibrium, which means it's not accelerating, the frictional force and the pulling force must balance each other. So I can write that mathematically. The kinetic frictional force is equal to the pulling force. And I can also write a vertical equation. The normal force is equal to the weight. If I know any one of these forces, I can use these equations to figure out the others. The horizontal and the vertical forces are independent of each other. They may be related to each other, but they are independent. Now, let's approach a mathematical expression for the frictional force from a practical experience perspective. In many cases in physics, you can begin to grapple mathematically with expressions by applying a bit of common sense. And I'd like you to begin to develop the habit of using your everyday experience to see if what you write down mathematically makes sense to you. So let's apply this to the frictional force. Experience tells us that the rougher the surfaces are, the more frictional force is exerted. Numerically, we indicate surface slickness using what we call the coefficient of friction, mu. Low numerical values for mu mean slick surfaces, whereas high numerical values for mu mean rough surfaces. So we expect the frictional force to be directly proportional to mu. This way of writing things, FF with a tilde mu, means directly proportional to. Also, the harder the surfaces are pressed together, the higher the frictional force is. And how hard the surfaces are pressed together is given by the normal force. For instance, an empty bookcase is easier to scoot across the floor than a bookcase that's filled with books. The one that's filled with books has the bottom of the bookcase and the top of the floor pressed more firmly together, and as a result, it's harder to scoot the bookcase across because the frictional force is bigger. So we expect the frictional force to be directly proportional to the normal force. So now let's put these two together. Oftentimes, we can simply multiply together the things that we expect to affect our outcome and get some result. And that's what we're going to do in this case. We're going to say that the frictional force is equal to mu times the normal force. This is the central equation of this lesson, one that will appear again and again in this course, and you should memorize it. If kinetic friction is involved, then I'm going to add the subscript k to the coefficient and to the frictional force. If the surfaces are not moving with respect to each other, then I'll replace the k with an s for static friction. On page 54 of your textbook, your authors give you a table with typical values for coefficients of friction. You have a set of numbers that are for static friction, and you had a set of numbers that are for kinetic friction. What I want you to see is that, for the most part, the coefficients of friction are between 0 and 1, with kinetic friction smaller than static friction. And what that means is that it takes more force to get something started moving from rest than the force that's required to keep it moving. Sometimes you'll get these numbers as part of a problem statement, or you may be asked to calculate the numbers. So let's apply this knowledge to a particular example. Example 8.1 reads this way. The coefficient of static friction between a 6,500 Newton block and a level surface on which it rests is 0.73. What horizontal force must be applied to the block to make the block move? Let's sketch a diagram and solve the problem. Here's my free body diagram. They tell me that I have a 6,500 Newton block, and what they're telling me with that number is the weight of the block. The block weighs 6,500 newtons. They tell me that the coefficient of static friction is 0.73. And now we want to know, how hard do I have to pull? In other words, what is FP in order to get the block just to move? What I claim is that FP has got to be a number that is at least equal to the maximum static frictional force. We know that the static frictional force is going to be the coefficient of static friction times the normal force. Since the object's in equilibrium, the normal force must be equal to the weight, because the object is not accelerating vertically. So I know a number for the normal force, and I know a number for the coefficient of static friction. So I can figure out what the maximum static frictional force is. It's going to be mu 0.73 times the normal force, 6,500 newtons. And now you need your calculator, and you put those numbers in and work it out. What I find is that the maximum frictional force that this surface can exert on the box is 4,745 newtons. Because the maximum frictional force is 4,745 newtons, then to get the box to move, I'm going to have to exert at least a 4,745 Newton force. If I exert a larger force, the box is going to break free, the object is going to begin to accelerate to the right, and I will have put the object in motion.